Heat exchangers. What is a heat exchanger? Heat exchanger transfers heat energy from one medium to another. Heat can only flow from a higher temperature region to a lower temperature region. Heat exchangers are called by various names such as coolers, heaters, condensers and evaporators. Theory of heat transfer. FURIOR'S law of heat transfer. The heat transfer rate of a conductor, which is in its steady state, is proportional to its cross-sectional area and the temperature gradient. Consider transfer of heat from fluid to a flat plate, and from the plate to another fluid, as shown. There is a thin film of almost stagnant fluid layer on each side of the plate, called boundary layer. Practically, heat transfer through the boundary layer is by conduction only. The quantity of heat conducted through the film of fluid, per unit area of surface, in unit time, for unit temperature drop across the thickness of the film, is expressed by the coefficient of heat transfer. Types of heat exchangers. In the shell and tube type heat exchanger, one medium flows through a set of tubes and the other medium flows on the other side, thus heat transfer takes place across the tube walls. In the plate type heat exchanger, a set of corrugated plates are tightly packed with spaces in between. The different mediums flow on either sides of the plate and heat transfer takes place across the plate. What is Reynolds number? This number is a dimensionless number, and expresses the ratio of inertial forces to viscous forces. Laminar flow is a very orderly flow, in which the fluid particles move in smooth layers. Fluid velocity variation is approximately parabolic, being a maximum at the center and zero where the fluid is in contact with the pipe or plate surface. In turbulent flow, fluid undergoes irregular fluctuations, or mixing, in contrast to laminar flow. The speed of the fluid at a point is continuously undergoing changes in both magnitude and direction. Turbulence is measured in Reynolds number. Turbulent flow is marked by higher Reynolds number, and laminar flow is marked by lower Reynolds number. For efficient heat transfer, turbulent flow is the best, but erosion is higher as a result. Parallel flow arrangement. In the parallel flow arrangement, the hot and cold fluids enter at the same end, flow in the same direction, and leave at the same end. This type is not normally used in marine practice. Two major drawbacks are there in this arrangement. One is the large temperature difference at the end causes large thermal stresses. Second is the temperature of the cold fluid exiting the heat exchanger never exceeds the lowest temperature of the hot liquid. This design is used when two liquids are required to be brought nearly the same temperature. Counterflow arrangement. In the counterflow arrangement, the fluids enter at opposite ends, flow in opposite directions, and leave at opposite ends. Some advantages are there. More uniform temperature difference between the two liquids minimizes the thermal stresses throughout the heat exchanger. More uniform temperature difference produces a more uniform rate of heat transfer throughout the heat exchanger. If the heat exchanger is well designed, the outlet temperature of the cold side can even be higher than the outlet temperature of the hot side. Cross-flow arrangement. The direction of fluids are perpendicular to each other. Exchangers such as air coolers for diesel engines, superheaters, or tubular gas heaters in boilers use this arrangement. This design aims to maximize the heat transfer surface area. All the previous flow patterns can be included here. Practically most heat exchangers use mixed flow to obtain best possible characteristics. The turbulent flow of fluid can be improved here. Shell and tube type heat exchanger. The shell is usually made of grained cast iron, with surfaces machined as required. Gunmetal of fabricated steel may be used as alternatives depending upon requirements. End boxes with end access covers are at the same material as the shell. Sacrificial anodes and electrical contact strip are fitted to minimize corrosion. The tube stack is made up of stress-relieved aluminum brass tubes, expanded into naval brass tube plates. One plate is fixed, and other end is free to allow for expansion of the stack. Brass circular baffles give radial flow to the fluid, and support to the tube stack. Deciding the capacity of heat exchangers. Most heat exchangers are sized to provide about 30% more surface area for heat transfer than that required. This extra allows for to cope up with fouling and deposits, thereby increasing the period between openings. To cope up with the plugging of defective tubes. Usually 10% is the limit before the tube stack requires changing or the tube renewing. To cope with overloading of the engine for short period. To cope up with abnormal seawater temperature. Let's discuss about the causes of tube failures. General wastage. This is due to acidic water, which prevents the formation of a stable oxide film. Impingement attack occurs due to turbulence. Deposit attack. The metal under the deposit becomes erodic to the surrounding area and starts to corrode. Anaerobic attack. Bacteria reacts with tube material causing local attack leading to pitting or tube perforation. Erosion. Due to abrasive solids such as sand, or air bubble in the coolant. Plate heat exchanger. A plate heat exchanger uses a series of thin plates to transfer heat between two fluids. This consists of a pack of thin rectangular plates with portholes, through which two fluid streams flow, where heat transfer takes place. Other components are a frame plate, a pressure plate, upper and lower bars and screws for compressing the pack of plates. When the package of plates is compressed, The holes in the corners of the plates form continuous tunnels, or manifolds through which fluids pass, traversing the plate pack and exiting the equipment. The spaces between the thin heat exchanger plates form narrow channels that are alternately traversed by hot and cold fluids, and provide little resistance to heat transfer. There are some unique advantages such as flexible thermal design. That's mean plates can be simply added or removed to meet different heat duties. Easy to clean. Good temperature control and better heat transfer performance. Plates and gaskets. The most important and most expensive part of a plate heat exchanger is its thermal plates, which are made of metal, metal alloy, or even special graphite materials, depending on the application. Stainless steel, titanium, nickel, aluminum and tantalum are some examples commonly used. The plates in most applications have corrugations that exert a strong influence on the thermal hydraulic performance of the device. The channels formed between adjacent plates impose a swirling motion to the fluids. The sealing of the plates is achieved by gaskets fitted at their ends. The gaskets are typically molded elastomers, selected based on their fluid compatibility and conditions of temperature and pressure. Nitrile rubbers are the materials generally used in the manufacture of the gaskets. Leakage telltale arrangement is shown here in both types of heat exchangers. In case of breakage of gasket sealing, this will facilitate to locate leaks. Thank you for watching. See you in my next video.